Welcome to our number theory lecture. Today, we are diving into the fascinating world of congruence relations and their properties. If you have ever wondered how your computer securely sends messages or how a clock resets after 12 hours, you are already thinking about modular arithmetic. We will build this concept from the ground up, so do not worry if it is completely new to you. Let us get started. Now that we know what we are studying, let us look at how it works in everyday life. Imagine you are looking at a standard analog wall clock. If it is currently 10 o'clock and you wait 5 hours, the total time is 15 hours. However, the clock face does not have a 15 on it. Instead, the hour hand points to 3. In the world of clock math, 15 and 3 are treated as the exact same position because they differ by exactly one full 12-hour cycle. This idea of numbers wrapping around after reaching a certain limit is the heart of what mathematicians call a congruence relation. We are essentially saying two numbers are the same if we only care about the leftovers. Before we move on to the formal math, let us see this with a concrete visual example. Here, we have a standard 12-hour clock face. Notice the two arrows? The longer arrow represents a 15-hour journey, starting from the top. It completes one full revolution and lands on the 3. The shorter arrow represents a simple 3-hour journey, which also lands exactly on the 3. The visual wrapping of the arrow perfectly illustrates how the modulus, which is 12 in this case, resets the count. Because both journeys end at the exact same position, we can visually prove that 15 and 3 are congruent modulo 12. Now that we understand the visual intuition, let us look at the formal mathematical notation. In formal number theory, we say that an integer a is congruent to an integer b modulo n if they leave the exact same remainder when divided by n. The formula on screen shows exactly how we write this. The variable a is our first integer and b is our second integer. The number n is called the modulus, which is just the size of the cycle or batch we are using, like the 12 on our clock. The symbol with 3 horizontal lines simply means is congruent to. If you increase the modulus n, you are simply making the cycle larger, which changes when the numbers will wrap around. This notation we just saw leads us to a strict mathematical definition. The formula on screen states that the modulus n perfectly divides the difference between a and b. The vertical bar means divides evenly into without any remainder. If you subtract b from a, the result will be a perfect multiple of n. This is the core test to see if two numbers are congruent. If you increase the modulus n, the difference between the numbers must also increase proportionally for them to remain congruent. This definition is what we use when we need to prove a congruence algebraically. Building on that strict definition, by rewriting the division concept as a multiplication equation, we get this highly useful linear form. Here, k represents some integer, which could be positive, negative, or 0. This tells us that to get to the number a, you can start at b and jump forward or backward by multiples of the modulus n. As the integer k changes, you generate an entire family of numbers that share the same remainder. If k increases, you are simply taking more steps around the cycle, but you will always land on a number congruent to b. Before we move on, let us see this with a concrete example. We want to test our understanding by verifying if 38 is congruent to 14 modulo 12. We are given the numbers 38 and 14 and our modulus is 12. We need to prove whether or not they belong to the same position in a 12-step cycle. To do this, we will rely on the fundamental definition of congruence we just learnt. We start by setting up the subtraction of our two numbers. We are finding the absolute distance between 38 and 14 on the number line. This distance will tell us how far apart they are. Continuing with our calculation, we find that the difference between the two numbers is 24. Now we must determine if 24 is a multiple of our modulus, 12. We do this by seeing if 12 divides into 24 without leaving a fraction. This is a simple mental math check. We can clearly see that 24 is exactly 2 times 12. Because there is no leftover fraction, 12 divides 24 perfectly. The integer 2 represents the number of full cycles between the two values. Since the difference is a perfect multiple of the modulus, the condition for congruence is met. Physically, this means if you wrap a tape measure around a cylinder with a circumference of 12 units, the marks for 14 and 38 will land on the exact same line. So, we have proven that this specific congruence holds. This brings us to the broader properties of congruence. Congruence behaves very much like the standard equal sign you're used to in algebra. Because it shares these traits, it is known as an equivalence relation, which is just a fancy term for a relationship that groups identical things together. First, it is reflexive, meaning any number is always congruent to itself because the difference is 0 and 0 is a multiple of any modulus. Second, it is symmetric, meaning you can swap the left and right sides freely. Finally, it is transitive, meaning you can chain congruences together. These properties are what make modular arithmetic so powerful and consistent. Now that we understand the basic traits, let us look at how we can manipulate these equations. Beyond the basic equivalence traits, you can also add or subtract the same number from both sides of a congruence, just like a normal algebraic equation. The formula shows the addition property. If you start with two numbers, a and b, that are congruent modulo n, and you add the exact same integer c to both of them, the new sums will still be congruent to each other. The balance of the remainders is perfectly preserved. If c increases, both sides shift equally. Following the addition property, we also have a rule for multiplication. The formula on screen is the multiplication property. If a and b have the same remainder when divided by n, multiplying both of them by any integer c will produce two new numbers that also share a remainder. This property is incredibly powerful because it allows us to simplify massive calculations by replacing large numbers with their smaller remainders before multiplying. It keeps the math manageable. If the multiplier c increases, the raw numbers grow rapidly, but their cyclical relationship under the modulus remains completely intact. Now that we have these properties, let us apply them to a more advanced problem, where calculating the raw number would be tedious. We want to find the remainder when 7 to the power 4 is divided by 5. Calculating 7 to the 4th power directly gives a large number, but we can use congruence properties to make it easy. Our strategy is to shrink the base number first and then apply the exponent. We start by simplifying the base number, 7. When you divide 7 by 5, the remainder is 2. Therefore, 7 and 2 are congruent modulo 5. We can now replace the 7 with a 2 in all our upcoming calculations. Continuing with our simplified base, we will build our way up to the 4th power step by step. Using the multiplication property of congruence, we can square both sides of our relation. This means 7 squared will have the same remainder as 2 squared when divided by 5. We evaluate 2 squared to get 4. Since 4 is already smaller than our modulus 5, it is its own remainder. So 7 squared is congruent to 4 modulo 5. We are now halfway to our target exponent. To reach the 4th power, we square both sides of our previous result. By squaring the squared value, we effectively multiply the exponents to get 4. The math remains incredibly simple. Let us finish this calculation. We calculate 4 squared to get 16. Finally, we need to find the remainder of 16 when divided by 5. Since 15 is a multiple of 5, the leftover is exactly 1. Therefore, 16 is congruent to 1 modulo 5. By chaining our congruences together, we can conclude that 7 to the 4th power leaves a remainder of 1 when divided by 5. We found this final answer without ever having to calculate that 7 to the fourth power is actually 2401. This shows the true physical power of modular arithmetic. It keeps numbers small and manageable while preserving the exact cyclical position. Now that we have used these properties to solve problems, you might wonder why mathematicians spend so much time developing a system just to track remainders. The truth is, congruence relations are the absolute foundation of modern digital security. Every time you send a secure message, log into your bank account, or buy something online, your computer uses public key cryptography. This is a method of locking data using complex math. These encryption systems rely entirely on modular arithmetic to scramble data into massive numbers and unscramble them using specific moduli. Without the properties of congruence, it would be impossible to perform these calculations quickly, and all digital communication would be completely vulnerable to hackers. We have covered a lot of ground today, so let us review the key takeaways. First, a congruence relation is a mathematical way of grouping numbers based on their remainders when divided by a specific cycle length, called the modulus. If two numbers have the same remainder, they occupy the same position in that cycle. Second, by mastering the properties of congruence, such as addition and multiplication, we can simplify complex arithmetic with massive numbers. Finally, we saw that this is not just abstract math, it is an essential tool for everything from basic number theory to advanced computer cryptography. You now have a solid understanding of how congruence relations work. Great job today.